Our first presenters are Florian Knig and Alexander Soups. Florian joined WaveGate in 2010 as a software engineer for X-ray and CT imaging, and has had roles in sales and applications, and he has been in product management for just over a year now, with a diploma and master's degree in electrical engineering. Alexander is a consulting engineer at WaveGate with over 20 years of experience in X-ray and CT business with a PhD in computer vision. So welcome, gentlemen.
Thank you very much, and thank you for the kind introduction. I'm happy to talk to you today a little bit about what we call finding the needle in the haystack, the use of AI in defect analysis. And to get ourselves started here, I want to just briefly talk about like who we are, what we do. So as mentioned before, we are part of Baker Hughes, the WaveGate technology business. WaveGate is all about industrial inspection solutions, right? So we are a global leader in non-destructive testing. We have 10,000 and more customers worldwide. We have a worldwide representation. We have a lot of experience in different fields of NDT, non-destructive testing, over 125 years. We basically, you can group it into the radiography side of things, so 2D and 3D radiography, CT and X-ray, which is also where myself and Alex are located within our business, and which is our main focus. Nevertheless, we also do offer other solutions when it comes to ultrasound testing, as well as visual testing, right? We are mainly a hardware provider. We provide all those machines that you need for those kind of testings, but of course we also have a huge portfolio when it comes to software, which is our main focus area for Alex and myself. And this is what we want to talk to you about a little bit more today. How do we use AI in this industry and in this non-destructive testing environment? So quickly, like, what do we want to talk about today? First of all, we want to have a bit of a motivation, like why do we inspect, right? Like we are all about inspecting parts, inspecting customer parts, but why do we do that in the first place? Second to that is like once we have inspected something, we get a lot of data, but what do we do with this data? How do we actually recognize defects in the data, and how do we make use of the data for our customers? As a third thing, then we want to talk about the automation side of things. Like you can of course do manual recognition of defects, but how do we automate that? How is this done? And then we go into the gist of it. Alexander will cover ADR, AI, machine learning, neural networks, and especially like how does it translate to our problem statements that we have in the NDT space. And last but not least, we want to talk a bit of the practical side, right? The famous German one said, "Gray is all theory," and we want to give you some real-life examples of how we can actually use AI and ADR, so automated and assisted defect recognition, to make decisions based on inspection data easier and quicker. So let me get started. Why do we inspect? It's simple. Like we want to make things better. We want to make parts better. We want to be faster in our production, and we want to improve the performance of those parts. So we're talking all about like quality assurance and in this non-destructive testing field. And of course, the non-destructive testing is always seen, or testing in general is always seen as a necessity, like as a cost driver, right? So we want to inspect as quick as we can, as cheap as we can. But of course, we want to also ensure that we inspect as reliable as we can, right? We want to make sure that if we inspect a part, we do see all the defects that we're looking for. And as I said before, like, so the huge drivers for ourselves is like, we want to make sure that we are cost efficient when it comes to the inspection of parts. We want to make sure that we see all the defects we're looking for. So we're looking for structural defects, looking for material defects like porosities and castings, or broken solder joints in electronics. We also cover a lot of the dimensional and metrology side of things, so measuring parts, making sure that they actually fit, that the actual dimensions are correct. And also what we can find with our technology is like we can see if manufacturing equipment is actually trending, if we have a drift of certain sizes or certain defects, if over time, so we can then loop that back and say, well, there's something wrong with your manufacturing equipment, right? But we do not only work in the quality assurance side. Also on the in-service side, we look on the integrity and liability of parts. We also, just as a side note, we do offer a lot of inspection services as well. So it's not necessarily the need to buy a machine. You can also contact us if you're looking for any inspection services to get started. Why are we doing that? Or giving some examples, like if you have a failing airbag, if you think about blown aircraft engines, burning electric vehicles, all these kind of things happen because something is wrong with one or more of the parts within those assemblies. And what we try to do and what we are doing is helping our customers finding those defects before they become a problem, right in production, or even before in the research and development of those parts. Of course, on the right-hand side, you can see the greater the risk, the greater desire for inspection. I think it's pretty clear that in the aviation industry, for example, failures of parts are most likely catastrophic, right? Whereas in the, for example, automotive industry or consumer electronics industry, there might be different risk aversity in these industries. And of course, there the cost is a major driver there. But for sure, like if you think about the aviation industry, we clearly see like that the main driver is the security and the safety of the part. So now that we talked about why do we inspect and what do we inspect, it's like what do we do with the data? Like, and speaking for myself, being in the CT and X-ray industry for quite a while, what do we do with X-ray images? Like when you go to the doctor, it's nice to see an X-ray image, but there's not much value in it for yourself because you're not a trained expert on X-ray images. And so am I. Like when I look at a medical image, I struggle. So you need a lot of domain knowledge to actually interpret what you're seeing. So a big challenge in the ND industry, not only for X-ray, but in the broader scope of the ND industry, is the resource burden. Like we need skilled and certified operators of our machines to make to in the end judge whether or not a part is good or not, right? It's as I said before, it's a challenge is of course always the cost and the perception. What we clearly see is that we have an aging workforce, and our customers have more and more problems in finding new skilled operators for our machines. Data retention is also a thing that is getting more and more important, especially in strictly controlled environments like the aviation industry, where you have to keep the data, inspection data for sometimes tens of years. So that's a big challenge, especially when you generate a lot of big data sets and the whole data flow. There are, of course, also technical challenges. Like every human has its flaws, and you will never find anybody that will have 100%. Is 100% correct when it comes to interpreting data, right? So and also it's tiresome. If you look at the screen for 8 hours, it is really tiresome. So it really takes a lot of skill, but errors are kind of always happening. So that's all of those challenges lead us to the conclusion that the more we can automate, the better, right? So automation of analysis for NDT data is a key driver for our software development that we've been doing over the last 20 or even more years. Of course, I think it's clear that if we do it right, we get a huge speed improvement. Typically, the machine is always faster than the human. We can also, again, if we do it right, and we talk about that later, what that means, we can improve the quality. Like if we have the right algorithms, if we have the right technology, then we can make sure that the quality of the inspection is better than with a human operator, right? Because for sure, a computer doesn't get tired if it's doing the same thing over and over again. Also, the resources that we need, the skill level is a different one when we talk about automated or at least assisted defect recognition. I don't in the matter for time, I don't want to go into every detail here, but there's a lot of things to consider, of course. Like we have to make sure that the performance of the algorithm or network or inference or whatever we want to call it that we're using is understood, right? So what good is an automatic analysis if you don't trust it? Then you're probably not going to use it, right? Also, I think a huge driver for us is like the question: do we automate completely or do we assist the operator, right? especially in very conservative industries that we're working with, like the aviation industry. There's a lot of hesitance in completely relying on an automated system, but we can do a lot to assist our customers in finding the defects easier and more reliable. So these are the main takeaways. Just quick overview of our history. Like, we have been doing ADR, so assisted or automatic defect recognition, for quite a while. We started in the 90s. We developed, well, when I was back in high school, we developed the first ever commercial X-ray ADR machine, meaning a completely automated setup to find defects in castings for the automotive sector, looking at weldings and at inclusions. We have since then, in the 2000s, we have entered the market for the so-called Phoenix X-ray systems, so a line of 2D systems, 2D X-ray inspection systems, with what we call XC². It's a comprehensive suite of tools that help you to automatically inspect electronics, right? And we have a few examples of that later on if we talk about the practical examples. So what we can do here is, like, we can do automated inspection of solder joints, of PCBs, and so on and so forth. Now, of course, as we all know, in the last years, I would say there has been a huge development when it comes to the tools that we have available for these kind of challenges, which is the whole AI, machine learning, right? Everybody is aware that there's ChatGPT and everybody's very excited. I think there's also a lot of what I would call AI washing out there. So we have to be careful, of course, that we really understand where's the benefit, especially if we're in sensitive cases where we are, where really the safety of an airplane depends on it, right? We want to make sure that we understand the technology and we're not just doing something where we don't have trust in the results, for sure. So with that said, I want to talk just a little bit about what's the foundation before we get into before Alexander goes into the I think core of this presentation when it comes to the AI. I want to talk just a little bit about, like, what's the foundation for our algorithm that we will presenting. And one thing that is, I think, very, very important to understand is, like, you can have the best neural network, you can have the best algorithm for image processing. If you don't have good data coming in, then you will not have good results coming out. So what's called the GIGO, so garbage in, garbage out, right? So our first approach always, when we tackle such a problem with the customers, like, we try to get the best possible outcome out of our machines, whether it's X-ray, whether it's ultrasonic, whether it's visual inspection. We try to optimize all the settings of in this example here, CT scanner, to make sure that the image quality that we get out of it is as good as it can, because of course this will always influence the outcome of the later inspection task. So, and there's a couple of questions we need to answer, like, what does your data look like? Like, do you have good quality data, as I said before? Has it been optimized? Also, do we actually know what we're looking for? I think that's a huge problem that we often see is, like, well, we know the part isn't working, especially in the electronics industry. We probably know that it isn't working, but why isn't it working? Like, what are we looking? What are the defects we're looking for? Because the more you can narrow it down before you even go into the defect recognition, the easier it gets in the end, right? So, and AI specific, I wanted to mention one thing, like, it's all about the data, right? All these AI networks that we have created together with customers rely on input data. If you have no data to train your models, then they will not perform the way you want them to do. So the data management aspect of it, I think, is a of huge importance. Sometimes I would even say it's the data management might be even more important than the actual model, because nowadays there's a lot of things, and Alex will cover that later on. There's a lot of things that are available today. Like, technology has been evolving incredibly fast in the last years, but it doesn't help you if you don't have the data to feed it, right? And with that, I'll hand it over to Alexander.
Yeah. Okay, so I will continue with the same screen sharing. So actually, what you see here is, let's say, different views on the same thing. So if the people say AI, they probably mostly mean the deep learning neural network things. But actually, if you look on the Wikipedia, what is AI, what is machine learning, the ML, and what is the deep learning, the DL, you will see this kind of three circles that are on the bottom right place. Yeah, and if I go first to the very large circle and to the very left, and for example, if I take background abstraction for the images, yeah, you are doing X-ray inspection and you would like to detect in which portion of your image is the part itself, yeah. So basically, in our world, the background is white and the part itself is darker, a kind of grain transitioning to black. And if I just do very simple background abstraction, that is good enough maybe for many cases, but actually for most of the cases, it would be not good enough, as you will be very dependent on this white level. And if you take the next system with a different X-ray tube or whatever, you will need to adapt your algorithm for this new background abstraction. Yeah? And this kind of rule, how to detect the parts or the defects in the parts, and I will give you some examples of what can be the defect later and how this is visible in the image for electronics. This kind of rules are so-called rule-based algorithms. These are classical computer vision algorithms that I have learned in the university a while ago. And those algorithms, they became with the time and with open source software, which is very important, they became more and more complex. And then the people start to think about some dictionary learning, about principal component analysis, where you have many features and you need to correlate and you don't know upfront, you cannot describe it visually. But if you do some mathematical operations, you would be able to detect and to line up those principal components. And based on that, it's a totally different dimension. You cannot describe in many cases. And based on this, you can classify if it is a defect, what is the defect size, and this kind of things. Yeah. And those things were evolving with the time. Yeah. And the people finally got, because the computational power was available, the people finally got to deep learning networks. So with a network, we mean really let's say a very simple morphological operations or arithmetical operations, even in case of image processing on a pixel level. Lauren, can you go to the next page? Yeah. So, and those operations you can see here. You have input variables on the right, left-hand side on the top. You have input variables. In a very simple convolution or even adding of the variables, yeah, for example, the top green layer, the hidden layer, the top dot of that will just add the variables 1 to 4, and that is already a kind of neural network operation. Yeah, and then you can also generate a value for the second green dot, and you can, after that, you can combine the green dots to the output. Yeah, for example, if a value is bigger than 1 or lower than 1. So, and you can, instead of having one hidden layer, you can have two hidden layers between your input and the output. And you can imagine if the input are your pixels in your image, like you have on this classification example for handwritten things, yeah, in this case, these are numbers. Your input are pixels in this image matrix, yeah, and your limited output is a decision if it is a 1 or 2 and so on. Yeah, or maybe if it is something or nothing. And this something or nothing that can have a lot of variations. If it is noise in the image, yeah, the noise can be also stronger or less strong. But if you correlate those picture elements, the pixels, to detect if it is just a noise or something significant, you might have this kind of very deep and very deep in this direction and very tall networks, so you can get a lot of input variables, and also in some cases also some many output variables. So exactly on this page, you see on the right-hand side, you see an example of our implementation of neuronal network for our visual colleagues. And in Waygate Technologies, they have implemented this deep learning network and have released a product for gas turbine inspection. And you see the defects, they are marked as this very high significance, they are marked with dark blue. With low significance, they are marked with actually in this example, one big light blue area. And so for this kind of things, because you can imagine if you have a lot of neurons in the hidden layers, you would need a lot of images to train those hidden layers to actually generate the weights, how you make your connections. On the right-hand side, on the top, you see if you compare these different approaches, the very old-fashioned rule-based algorithm with the very modern deep learning algorithms and networks, you will see the if a human operator has not 100% performance because of the reasons Florian already mentioned, yeah, they can get tired, they can get not well trained or whatever. Yeah, you can have only a certain performance level. In many cases, it's still better than the performance level of simple rule-based algorithms. But if you deepen your neural network, you will get a performance increase. But for that, you would need much more data to train. Yeah? And the magic is, as Florian rightfully said, in the data preparation, but also on how you design and stack your networks. So on the top, on the bottom, you see an example of encoder decoder network with a lot of input and also a lot of variables on the output side. And you can do whatever comparison, you can do feedback loops between those things, and by that you can train your network to do the right inspection, to detect the right things. Next page, please. And here you see a typical diagram how we make the things practically work. So as first of all is data acquisition. You should have a good data quality. For that you should have a CT machine or 2D machine for electronic inspection, for example, in very good state. Then you need a very experienced operator to annotate your data. Where is the defect? What sizes has the defect? And if you have a lot of this data, of these labels, you can apply additional so-called data augmentation, because still we have limited amount of images. The more images, the better, but still we have very limited amount of images. For example, one defect can be oriented in this direction in one image, but in the next part, what we don't inspect with X-ray, because we just don't have this part, the defect can be oriented in the other direction. But by image augmentation, in this case, it would be just a rotation of the image. You could improve heavily your data set to be prepared to whatever cases you can envision for your case and for your inspection needs. If we have all these things, yeah, if we have set up our software architecture to do data augmentation, if we have the annotations on the right place, and it should be reviewed, yeah, we can start the deep learning, yeah, and after that, we will have the model, yeah, it can be evaluated by some experts, what kind of performance this model can have for defect detection, yeah, if the number of true positives is good enough and the number of false positives is very low, it would be ideal case. Yeah? And after that, you can start inferencing, so applying your model on a real world inspection task, so giving the model to the production. Yeah. And for example, you will have the segmentation of the images, and you would be able to measure the defects and so on. Some important question. Ground truth should be good. We already mentioned this. So, and you see it's a really practically measured example. If you have one operator, yeah, one inspector, you would get a certain quality of your ground truth. Yeah, if another people would label the same data, and typically you can average between those people or discuss the differences, yeah, and you will get improved quality. And if you can increase the number of operators to 3, 4, 5, you can still further improve your data, yeah. And we would consider ADI successful if we would get the same false positive rate or the same true positive rate as if the real operator, real human would do this. If we have this on the same level or slightly better, typically the ADR goes into production. So another very important aspect, it's intersection of union, and this is illustrated on the very right. So, for example, the red is the ground truth, and the blue is the output of the neural network. If it is like it is on the image, it's an important question. Do we get the defect? Is it considered to be detected or not? Yeah, this kind of things, you need to tweak up and you need to think up front while prepare your software architecture for training and for inference later. Okay, so on this page, oh, something happened. So this graph, I hope exactly Florian can you maybe exactly make it a little bit lower. Thank you. On this graph, you see on the x-axis a false positive rate. False positive rates, these are things that were wrongly detected. And you see true positive rate. That are the things that are detected correctly, yeah. So the false positive rate should be ideally 0, and true positive rate should be ideally 1. So if we are operating in the top left corner of this graph, it would be very good, yeah. And to get to this corners as close as possible, we need a lot of data, yeah. And how to validate the performance? It's of course those ROC charts. It's a cycle time for your inspection general, including the scanning or taking the X-ray image. Yeah, these are different failure modes. For example, for electronics, it's a question: what does the defect mean? What is the implication of the defect in the real life? Yeah, and how stable is your defect detection? And maybe even how stable is your production? So, and if I talk about the NDE in general, so it's different people might have different perception, yeah. So maybe a business, so a commercial leadership would say no defects allowed, yeah. But reality is of course different. The quality guys would say I would like to see as much defects as possible because this would improve my quality of my parts, yeah. And then the persons say maybe sitting somewhere between those. So and then of course if there are some human factors, for example, the human might fear the ADR might eliminate the jobs, which is from our experience in our world is not the case at all, because it's the opposite. We are lacking the experts. Yeah, and also it can be also positive impact onto the inspectors. They don't need to look on every image. They just look on the very difficult cases. And by this, they're doing actually more interesting job, yeah? And it's less tiring by that. And also feeding back the ADR results in digital twins of the parts, yeah? In the digital twin of the production process. It's also a very important aspect because you would be able maybe in future to predict failure of the parts by that, yeah, or maybe to predict view the trends in the production and predict when do you need to tweak the production to go to the right direction again. So it's a lot of information ADR can give. But now we are coming to very practical examples in electronic inspection. On the right-hand side, you see, by the way, this was programmed with rule-based algorithms, and it's still alive. On the left-hand side, it's wire sweep detection. So the wire should be straight. It should not be broken. And those things are detected in the software since probably almost 15 years. Yeah, 15 years. On the right-hand side, you see voiding calculation in thermally conductive areas of the dies glued on the substrate. Yeah, and you need also to measure the voiding of the. By the way, ADR in very many cases that it comes together with some measurements. It's not only detection of the void, but it's also I need to measure the void. Florian, next page. So it's similar is for ball grid arrays, so for solder joint inspection. And also on the right-hand side, it's geometric fitting of the connectors. Yeah, so it need to be on the right angle, and this is also implemented with the rule-based methods. And before that, the ADR can help, the deep learning ADR can help to detect those things, and upfront, then we can on difficult image areas, yeah, that we can easily measure the angles, like in this example. So probably exactly we are coming to the end, and in the last time we have implemented also teachable ADR shallow learning, so with not very deep neural network and also very deep learning for different things in our X-Approver software, that is software platform for X-ray and CT inspection, which allows the operators to train the inspection, to train what kind of defects they are looking for, and to apply the trained models on the real parts. In this example, you see a battery, and you see the traces of the electrodes, and the task is here to measure what we call overhang of the anode over the cathode. Yeah, and those things, this is very important for battery quality due to different aspects. If the anode is shorter than cathode, then it may be a shortcut. It is not good for the battery. The car may start to burn. Yeah, this is the case. And exactly. So what things we can offer for battery inspection is overhang measurement. We can measure the angles of the anodes and cathodes and bending angles. Of course, if the anode is curling back somehow, it should be not the case. Yeah, and many different from our different customers from us are applying different quality rules to prove that the battery is in good enough quality, and this is by the tolerancing of different things, overhangs and angles and so on. And for that, we can also apply volume registration. So as a summary, very important to get good data to understand what is the defect, what are the defect metrics for your parts. Yeah, you need to think about what might happen in the production, what defects need I collect at what quality to be able to train my network in a very good way. You would need also to program in many cases some post-processing things after detection to measure the defect size, for example. Yeah, and on this you would be able to calculate the performance metrics in the production. And also maybe another things I did not mention, but it's very natural. Let's imagine you have in difficult cases, you will, and you get the significance, what we call the confidence level of your detection, also displayed on the screen. And in difficult cases, where the confidence level is low, you can get a human operator to look on the image and maybe to relabel the defect. And with this information, you can feed back the training as well. Yeah, so you will, with the time, you will improve your defect detection heavily. So that's it from our side. And AI is, we are just at the start of the journey, and the more data we get, the better would be the defect detection, but still a lot of work needs to be done to improve the architectures of the networks and the software architectures. Thanks a lot.
Okay. Thank you, Alexander and Florian. You're a little over time, but let's just do one quick question. I mean, X-ray has been used in electronics for quite a while. Obviously, you're adding computational tomography, CT, to it. Are there some really leading edge problems that X-ray CT can solve? And what does AI enable that hasn't been practical before in the electronics industry? Because
maybe I will start with the very last question. On one of the pages you have seen where the voiding calculation was maybe. On this page, it was a very complex structure of the object of the voids compared to the. It was overlaid with many different components. Yeah, there were wires, there were some, I believe, the hole, some chip on the top. Yeah, in these cases, you would need. It is very difficult to really do this with classical image processing methods to detect the voids and to compute the area. And AI helps in this case a lot. Of course, you need data to train the AI.
Yeah, and I think like a more generic answer is like we can improve the throughput, right? We're using AI and ADR. So we can really, because detection, like in many cases, is nowadays the bottleneck. It's no longer the acquisition time. It's really the time that it takes to evaluate the data. If you have hundreds and thousands of inspection points on your board, for example, and by leveraging this new technology, we are much quicker and much more reliable for sure, and much less operator dependent. I think that's the big trend that we see in this case.
To answer the first question, I would say computed tomography, especially what we call planar computed tomography, helps a lot to differentiate between those layers. Yeah, you would strict go to this layer with the void calculation. Yeah, and you would get an image that is much clearer for ADR to be inspected and to have a good defect detection there.
I would like to thank our sponsors once again, ASC and Amcor. And with that, I will wish everybody a great rest of their day and look forward to seeing you at a future MEPTEC event. Thank you for joining us.